Hello, back in business to show you some Raman practical microscopy. So how does it actually work when you go to the instrument? So in an ideal world, of course, I will show it to you with peculiar samples, but it's a bit like fiddly, and also I can only work the instrument by myself. So in a non-incredibly ideal world that we live in, I basically took some samples that I had to measure regardless, and in my day of sitting at the Raman and doing stuff, sometimes I recorded videos for you to actually use. So sorry if they're not perfect, they're a bit fiddly. There is a reason why I'm doing this lecture on science rather than doing big money on TikTok. I could actually use a better equipment, but it's a bit difficult to work it with a single hand while you're also trying to use the instrument. Also, this whole thing is on Google Drive because it was where I stored this remarkably heavy video, so I will have to do some fiddling while we are starting the video for you to actually be able to enjoy the presentations without going too slowly. But hopefully this gives you like kind of a feeling of all the stuff that I was discussing from a very theoretical point of view during the lecture. So how does the instrument actually work? This is the instrument that we have at our industrial collaborators at DSM, and it's a rainy show in via Raman microscope. So you see here the common microscope, but you can see that the chamber is pretty big. The feature of this thing moving around is very important. You're able to change the lenses depending on what you want, and in comparison to a normal microscope, you can see that this thing is remarkably big. This thing is a CCD detector of the Raman, and you have two different positions that you can switch because different radiations will need different grids. And all the way to the back you have the guide of the Raman lasers. So you can see here the warning, laser radiations, make sure you know what you're doing when you turn them on. This was the green laser, the other one is the red one, and the first thing that you do when you want to start the measurement is turn on your laser, which is fair. So it is a bulky instrument. You cannot do Raman with a teeny tiny equipment, especially if you want to do Raman microscopy, because you need to be able to have a laser that can be focused on a lens of a microscope, basically. So this needs the whole guide that you can see over here. I didn't open it because the instrument scientist would have killed me if I had opened all the optics, but the optics inside are exactly the one that I showed you during the lecture. So you have a guide of the laser, so you can see it here coming into the equipment, so you can actually see the internal guide of the laser going in the external guide going into the instrument, and then you have the outcome radiation that will come out of your microscope and get guided towards these two detectors. Depending on which radiation you're using, the grid that does the splitting of the energy will have to be different because the incoming radiation is at a different wavelength. And how does it actually look when you try to put a sample in? Not very much different from how it looks in a normal microscope. So you put things down, you make sure that you're at the lowest magnification, you're sort of there. You start to locate what you want to look at. So in this case, I had some samples from art conservators. Actually, these are pieces of painting. So you make sure that you put your things in focus. This instrument is very fancy, so it has like a focusing grid that you can actually use, and you can scroll in and out, and it goes in and out of focus. You can see that it also comes with like a scale bar. You can change the lighting, and you could see here that we actually had a very specific positions of the plate. So that thing that you see here is actually that XY stage, so it tells you exactly where you are at this crazy precision, so you could literally move if you wanted to move without having to do anything by hand. You could just ask the instrument to move the stage where you want it. This is particularly important for mapping, even though I will not be showing you mapping here because it takes a significant amount of time, and you will see how long does it take normally to do a measurement later on. And you can see here that we have controls of the optics. This is important because the instrument needs to be in alignment with the requirements. So if we are using a 532 nanometer laser, we need to stay with the specific grid and the specific detector that comes with the grid. If you mismatch the two, the instrument is not going to run, but this has a series of fail-safe, given that it's an actual commercial instrument, so it will refuse to run until you check that everything is in position. So now that you put your samples and you know that you are pointing more or less in the same, in the right point, because your cross section is at the right point, what you can do with the instrument is change the lenses. So I went here from a 5 pair to a 20 pair, a 50 pair in long distance focus. You can see here the label. So this means that this is far away from the sample, but it's still giving me a 50 pair magnification, which is nice. You can see that now we are completely out of focus, but we can tell the instrument, I change objective, can you bring me back in focus? And you can see that this clearly changed the height of the stage to bring us back, and then we can use the wheel to go back in focus. You can see that this is really bright, but you can see when we're out and when we're going back in, and when we're out and going back in. So of course at the moment the light against which we are doing the focus is pretty bright, so the easiest thing to do if you want to be able to put things in focus properly is lower the amount of light that you're shining onto your sample. Now this is a very fine scaling and the compound is not flat, so it's impossible for me to put it in focus all over because I'm looking too close. So I need to choose my fighter, I need to choose where do I want to be in focus, so where is this cross section in focus. That's the point where I really need to make sure that my instrument is in focus. It doesn't matter that the rest of the image is blurry. It could matter because you're trying to save the image, but for the purpose here, the fact that you can adjust the focus spot by spot is exactly what you want. So it allows you to take measurements that are in focus on a surface. The surface is uneven, like this is a piece of a painting dropped on a slide, so I cannot make it perfectly flat and even, and still the instrument doesn't particularly care. So how do we acquire a Raman spectrum? As I said, we want to stay on the right spot, so we choose where we go. So the crosshair will be the point where we do an acquisition, and the laser will be on when we switch the experiment on. You can see that this is the actual acquisition tab. So what you have in the acquisition tab is the choice to actually tweak your collection, right? So we are at the right configuration of the instrument. If I were to shift this, so change the edge but keep the rest of the detectors, this will tell me the instrument is not calibrated. If I'm in the right mix, so the right wavelength with the right grade and the right detector, then the instrument tells me we're fine. And here, this is the thing that you really want to tweak, which is the spectral range. So you want to choose your centroid. So if you choose the center of your shift, then this will immediately open as far as it can go in the collection range. So if my center is at 800, I start at 165 centimeter to the -1, and I collect all the way to 1076. Clearly, if I want to collect from here but higher than and 300, then I must do 2 collections, because this cannot go through a crazy spread. The spread is actually commanded by the grating. So if I'm centered at a certain energy that I'm expecting to get out, the grate needs to be able to split all of these frequencies. So if I want to do a higher collection, then I need to tilt basically the mirror that will focus the radiation, and make sure that we lose some radiation at lower wave number, but we keep the one that we actually want at higher wave number. So it could take you 2 collections to acquire all of the stuff that you want. There is also the possibility to do an extended grating, which we are not doing now, because then it will move the grate during the collection, so you can extend the range, but it's a bit more complicated, and sometimes it could be worth seeing into different collections. And here I do the acquisition method. So here is where I actually have to choose how long am I keeping the laser on. So here I expose my sample to the laser for 1 second. The laser power is at 5%, so I need to stay low, and sometimes in some testing you even stay way lower to make sure that you're not burning your sample. And to improve the signal to noise, what you do is you accumulate. So you collect the same spectral, so the 1 second exposure with 5% laser power, for, in this case, 50 times. So it's 50 seconds of collection, but you get a better signal to noise. And if I save this configuration and I run the spectrum, you will see that it will start collecting with a bit of a wibbly wobbly, and it will slowly improve. Now, this is not an excellent thing, that's why I'm calling this overly honest methods. This is not showing the best of the Raman spectra, but it is quite common if you're kind of like poking around to see potentially something, but you're not quite sure what, apart from some certain components. And you can see the whole curve here, which is what was promised to us in terms of absorption spectra. You see, while I'm collecting, the instrument is dark. I cannot look at the sample because the light must be shut off for the laser to go. But you can see here that the longer I collect, the better my signal is. So my black line there was a previous collection. Here I collected for longer, this peak is getting bigger. So if I was unsure if this was really a peak, of how many of these were actually peak and how many were noise, this gives me a better indication. So it does take 50 seconds to do the collection. Then the usual trick here, we didn't burn the sample, we saved the file, always important. So you save it. This is the spectrometer extension, so this is openable only by the software. If you want to have it open, you export your raw data, because we like to be able to replot the stuff that we do. And that's what we do. So you can also save it with metadata if you want it, but in this case I told it, please don't do that. So this is the protocol when you go spot by spot. So you choose where to go. You know how big your cross-section is, you even have the scale bar there. And you know that you only collect in that point. You don't collect on the whole area, it's just one point. So you might have to collect on several points if you want something statistical without doing a full mapping. This is another acquisition of Raman spectrum, but I promise you it's a decent one. So you can see here that I went to a completely different, another paint sample, but this one is blue. So once again, I decide where I want to stay at, and I start my collection by deciding where I want to stay centered, how many accumulations do I want, at what laser power. You can see I went down to 1%, and you start the collection. Now you can see here this is a bit more like what we were promised in the lecture, so you can see a decently strong signal, several shoulders, other peaks. And the purpose of the accumulation is that you can see this raggedy line is actually going smoother and smoother and smoother. The longer you collect, the better the signal to noise gets, because the Raman signal is inherently weak, so a longer collection gives you a better quantity. So again, we save the whole thing, we export our stuff to make sure that we keep the raw data, and off we go with our collection. Right? So this is a decent Raman spectra of something that I know I was looking for, I think this was Prussian blue, so I could know exactly where I needed to look for and if my peaks will match. So I'm not expecting something as busy as you saw for an actual biological molecule, because Prussian blue is inorganic, so it doesn't have infinite amount of peaks, but they're nice and defined, and I can spot them. And whereas the maximum thing you could tell me under microscope, only looking at the sample, was, oh, it's blue. Here I can actually tell you it's blue with this chemical fingerprint, so we can say for certain that this is the composition, right? So this is instead a biological sample, so I asked specifically to the guy that gave me this to give me some standards. So these are hyaluronic acid, actually, and a different concentration. Once again, I put it under the light. Here I decided to just do directly with a 20 pair long distance, the 50 pair long distance objective. But as soon as my thing is roughly into the light, I should be able to bring the sample into focus. So I go back, I look at what I see, which at the moment is not much. I have to focus it properly. So I make sure that we go to the right one. I make sure that I have enough light to start focusing the sample, because otherwise I don't see anything. And then I use my little scrolly bar to slowly put the sample nicely in focus. So this is our actual image, and this is the dry hyaluronic acid that is on the microscope slide. So you can actually see this texture because it's a dried concentrated solution. So here I actually ask, give me the standard, so I'm sure that even though I can find this in the literature, I know what I'm collecting against. And the reason I wanted the standard was also to be able to see if maybe I could see different concentration based on the intensity in the actual real sample. So what I wanted to do was collect the spectra, and this, in comparison to inorganic material, you can see it's immediately more busy. So it's a lot more stuff showing up. Don't mind the additional lines. The additional lines that you see here are just because I was collecting at the spectra. The red line is the actual one in collection, and as I told you, I wanted to make sure that I had my stuff from the literature. So we are collecting in this region, and this is a paper that I fished out to make sure that other people had collected hyaluronic acid of different length, so that I could compare what I could possibly get. And you can see that here we have this very busy spectra below 1500, and this is exactly what is showing in our sample over here. So if you look at the red spectrum, the match is very nice. Actually, it's more spread out because the thing on the paper was compressed to show you a longer wave number range, whereas here we spread to show everything, so I can actually see all the different peaks. So this is actually working pretty nicely, and I can be confident that I'm seeing everything that I'm supposed to be seeing. So this is the other overly honest method 2.0 version, in which you think, oh look, I was collecting this, I started collecting this exactly in this spot, This is the actual high wave number collection. So as I promised you, sometimes you actually have to do 2 to be able to collect everything that you wanted. First of all, here you're going to see what happens if you go dilly-dallying around and you think that you want to start things even though you're not in place. Right, this is something that you can do, of course, with a microscope. So given that it's a microscope, if I want to remind myself where was I while I was doing a certain collection, and maybe in a paper you might want to correlate a certain position with a certain Raman spectrum, that's perfectly fine. You can take a snap. So this thing will take a picture of what the microscope is looking at, and then you can just save it, and you make sure that you save it with the axis. So by saving it with the axis, you also have the scale bar, and that's going to make everyone much more happy because they know what they are looking at. You save it in a sensible way, and then you go on with your measurements. So you use the name, then it says it's been saved. Nice. So if from here I want to go into my usual collection and go back to the lower range, so you can see here my lower range is different from the one that I was using before because I'm happier cutting more lower wave number to be able to collect to a bit higher and maybe have some overlap between these two spectra, which is going to help with the data analysis. I change my range until I'm satisfied with that I'm in exactly what I wanted as start and finish. I check my acquisition. This was actually a peculiarly sturdy sample. So here I'm with 100% laser power, which is surreally high. So you can see in the scale, in comparison to videos that I showed you before, the intensity is skyrocketing because I'm using the whole focus of the laser. I can use all of the photons. I'm not cutting photons away to dump the power of the laser. And my 10 to the 6, 10 to the 10 Raman is still giving me a peculiarly strong signal. So here is the overly honest method in which I try to start, and this thing tells me the doors of the spectrometers need to be closed when you want to shut on the Raman. So if you want to cancel and continue with the laser shutter closed, you can do that. Otherwise, you're supposed to close the door. When you close it, you can see it actually interlocks. And when it interlocks, then I can retry, and this will turn on the laser. So it will open up the shutter, and now there will be laser radiation inside. Other reason why this is overly honest method is I was clearly burning the surface even though I couldn't see it in the contrast. So my thing that was fairly okay when I was doing the same collection on the same spot, now it's frankly all absorption spectrum. So this can happen. You need to be patient. You need to be like, okay, let's stop and let's do it again in another spot. And this can be an effect that can be either better or worse depending on the sample, depending on what you're looking at, depending if it burns very easily. Sometimes I collected some of my chemical samples in the Raman. They burn in a second because they are very teeny tiny crystals. So this was very big and sturdy. So sometimes it was actually better to shave off some of the surface with the laser to be able to actually catch molecules that were not oxidized by the air. So you can see it depends a bit on your sample. And this is a whole real biological sample. So I told you this was going to be busy. This is absolutely busy. This is exactly what I was showing you in the lecture. If you look at the black line, which was the thing that I was collecting before I moved into another position and I started with the red light. And the black line, if you think back and you look back at the lecture, you can actually see that yes, it's actually exactly the level of busyness that we were expecting, because here this is a real section of a mice, and I got the section, I'm using the section. As a chemist, I don't care, but when I looked at it, I can tell myself, yes, this is clearly a biological section, because there are a lot of biological molecules and macromolecules contributing to the signal. So the feature here is clearly the feature of my thing. I want to save my spectra because that's always nice, and you never want to get out of your big days of experiment with too few a sample. So this is how biological sample will look like, and we want to save all the data. And if I change the collection range, which I can always do when I want to make sure that I collect to higher wave number, can be useful. Again, this was particularly sturdy. In a point by point, I could use 100%. And I can start my collection. You can see that here, at higher wave number, we are away from the very busy point, but we still have a very strong signal. You can see the blue line coming up was a previous measurement that I was taking, which was remarkably strong. The reason why I'm going here was because, if you remember, I'm trying to track hyaluronic acid, and hyaluronic acid had this very peculiar signal. I wanted to stay in a position where it should actually show up nicely. So even with a short collection, when you can use 100% laser, you actually get a remarkably strong signal, and you can often see difference in how strong your signal is, or how featured, if you see different shoulders and stuff like that. So it actually works. As I promised you, this is not marked. This is not something that I'm doing because I know where to look. I'm just going around collecting the signal, and this is telling me, yes, you see it. So clearly the hyaluronic acid is there. So overall considerations is that this takes a bit of trial and error to figure out, first of all, where are the things you're interested of. Can you go in focus? One thing that I didn't show you, because it takes remarkably more time, is the mapping. So for the mapping, what you do is you bring your sample more or less in like a position that you want, with a certain objective, and then you keep track of a specific region, because you can do that using the coordinates of that very precise motion stage. You keep track of that region, you change the objective, and even if you cannot see the big picture anymore, the computer knows where to go to stay exactly in that position. Then it will make a grid of the region that you ask. The grid can be as tiny or as diffuse as you want it, and it will start moving the laser quickly through. The issue, of course, is when you move the laser and you have very fast collection. So usually you keep your acquisition to 0.1 second and you try to stay low with laser power. It's still a lot of acquisition, one after the other, one point after the other. So the thing that you risk is actually seeing a racking of the laser going through the grid, because it's burning your sample. This is easier if your sample is thicker. So remember, thickness of the sample, especially for biological sections, could make a lot of difference for the Raman, but often when you go into other type of microscopies, you tend to use a very, very thin slice. So it's a bit of an issue of what can you actually see and what can you actually prove. And given that you do a very fast collection, it's easier to do the fast collection if your power versus timing is optimized to give you the best signal to noise, and if the actual Raman signal that you're looking at is particularly strong. So this takes a bit of patience, but usually it works if your sample is actually meant for this type of measurements, and you can actually get something worth it out of these measurements. I know that if you are like, if you're looking at stuff that is better just imaged, you might as well do imaging. But when people ask you, can you prove to me that you have exactly this thing that you are claiming maybe with staining, but you cannot prove it with staining, because staining is just a color. This is not just a color, this is a fingerprint of a molecule, and it pops up by itself, unconcerned by the staining, in a very reproducible way. So if you want to discuss particular examples that are actually relevant for your research, please note them down so we can actually talk about it during the live Q&A. So you can drop to me the big questions, I have this and this, can I actually see this? And in general, if you don't want to discuss it during the Q&A, please reach out to me via email and we can figure out if actual Raman microscopy could do the trick for your specific scientific problem, or if it's better to actually use something else and more traditional. I hope you enjoyed, and I'll see you at the Q&A on Friday.